Yeah, thanks, Lalita. So this is actually a little bit out of the ordinary here. It's so it's more related to talk to coding. So I'm a coding theorist, so I try to present my view of things in terms of privacy. So this is joint work with my student Salman and my colleague Osvaldo. Okay, so let's start very simple to see that we're all on the same page. And I guess this is along the line of what Lalita had yesterday. So we look information theoretic quantities for generating a privacy utility trade-off. And I tried to make this a little bit clear, but maybe was a little bit lost yesterday. So let's start a very simple setting. Forget about privacy for the moment. Let's look at rate distortion. So is this a pointer here?
It's right on the top.
Okay, excellent. So, okay, let's look at a simple rate distortion setup. So xn is the source vector we want to compress. So we have a source encoder, we have some index w, we have a source decoder, and then we reconstruct x hat n. Okay, so this is typically what we have is we have a lossy compression. So x at n would incur some distortion compared to xn. So typically what this happens is the source encoder maps these bits to indexes. W of length n are symbols in bits. So these guys have length nr, these symbols here. And then the source decoder reconstructs the lossy version x set of n. So, okay, great. So this is lossy source compression. And now how do we measure this? Typically we measure this with a distortion measure, which is we first pick a single letter distortion measure, which takes a single entry of these vectors. And this actually is, and we can pick anything what we want. In the following we pick Hamming distortion, but you can look at mean square error or whatever. I mean, there are many options. But let's just leave it generic for the time being. We sum up over all n guys, take the expectation over both xi and x hat I with a joint distribution, and then we have this 1 over n to normalize it for the symbol.
I guess just to be clear for everyone, xn is assumed to be IID from some.
Yeah, exactly. Xn is assumed, they're all assumed to be IID. That's the IID assumption here. Right? So I guess we talk about this maybe in the end, so that's another extension to make a non-IID, which is actually more practical. So now,
or more generally, xn is anyway coming out of a distribution that you're assuming.
right. So this is assuming it's to be IID. I mean, we can only do IID so far for the rest of this talk, but it would be nice to extend it to non-IID, but even find rate distortion bounds to non-IID case is very difficult. I mean, there are some bounds by Gray, but and later by Zachi, but it's not so. They're hard to handle. But our goal is actually to extend. Actually, I have my postdoc is working on extending this right now to non-IID. But anyway, so this is okay. The goal is to minimize the rate. Again, forget about privacy again on this slide. So the goal is to minimize the rate. And so how this works is basically we take the mutual information between x hat and x and minimize over the joint distribution induced by the conditional distribution induced by the joint distribution between x hat and xn, x hat n and xn. Right, and we want that this expected distortion should be smaller than some prescribed distortion we want the system to be as a designer. So I give you a distortion and you give me back the minimal rate for this problem. Right, so this is rate distortion. And what we can do is this can actually incurs actually a test channel. So it's somehow related, this is somehow related to communication in a way that, so x has some noise, so it's basically a lossy version of x. X hat is a lossy version of x. So we can model this as a kind of simple binary symmetric channel here, where x is, now we look with the binary actually, x is the input symbol, x hat is the output symbol. And so we see some distortion here, which flips those bits randomly with these corresponding probabilities. And clearly makes sense, there is a distortion if a bit gets flipped, if we actually use a Hamming distortion as a measure. Yeah, I think they're all different definitions. I mean, in cover Tom is a different definition than in Elgamal, Kim. So maybe then this is a inverse test channel. So I think they have a opposite definition, but.
Because I always thought the idea was that you stick x hat in, you add independent noise, which is your quantization noise, to get back the original source x.
Yeah.
And so therefore the channel model, because here x hat given x, the channel noise, your distortion vector, the error vector.
It's a communication problem, right? Yeah. It's like what I put as a communication. Yeah.
Should be X given
Yeah, but actually, yeah, okay, that's the reverse. That might be true. I guess I found two different definitions. So if you check Harvard Thomas, so we had this discussion some time ago. And
Optimization is equivalent.
the optimization is equivalent, right? Because
Interpretation is different.
it's true. Yeah, I agree. I mean,
Okay, all right.
but now, and so what has this? Okay, this is actually the rate distortion function here. We can plot this. So if we optimize this here, we see that we get this expression. So this is if you have a binary source and x is Bernoulli 0.5. So we get this rate distortion function. We can have a closed form expression hp minus hd. Again, this is our hx here. So this gives us actually this function. And so again, what we can say is here we can pick a rate, and the corresponding distortion shows up here. All the points here are admissible. We're not able to design any codes here below this rate. And this is what Shannon told us in his source coding theorem, Lossy source coding theorem. Right? So now what this has something to do with differential privacy. So, and I only want to touch on this, and maybe because we really have no results. So what we can do is if we really compute the log, the LLRs basically, of the outputs, x hat here of this channel, where the inputs are slightly disturbed. So this x1 and x2, these are vectors which have a Hamming distance of 1. That means they only say if you are binary vectors, they only are different in a single symbol here. We can actually write this as a log 1 minus d divided by d. And you can see what's going on here. Clearly, if the d is big, then this privacy, this epsilon here, would be actually kind of small. And if the d is very small, right, then this epsilon would be big. But if the d is 0, then clearly we don't have any privacy guarantees, which makes sense because we would communicate x without any arrow to x hat. So now we can actually.
It's very interesting that you get this log 1 minus d over d for any.
It's a randomized response.
It's a randomized, yeah.
But if you think about it, that's our solution even over a range. And here he knows the
Yeah,
source,
because we
but
have
he still gets the same thing.
No, but in the problem we looked at, we have, there's a worst case source. So, I mean, like, one negative dominates the
right.
other.
Right.
One source is worse, so we only have to care about one source.
Right, and this is for all sources.
Yeah.
Yeah.
I mean, I think that's true.
Right. So and you can actually in IT speak, what we can do is we can actually bring in now the entropy. So we can get actually a relation between this. If we call this now a privacy mechanism in CS language, we can actually get a relation between this epsilon, this basically this log here, and the argument of the log, and this conditional entropy, right? Because conditional entropy is actually we only evaluate this binary this function, this entropy function, only on the positive for the x up to half. Otherwise, we can invert. But now we get this, and now we see a direct relation between conditional entropy and privacy in a way for the point-to-point channel. So for this small rate distortion problem here. So and you can see if this guy is big here, then if the conditional entropy of x hat given x is big, then we would have a very small privacy, or the epsilon would be very small here, right? So we have a relation between these quantities, between IT quantities and quantities basically in differential privacy here. So let's keep that in mind. So we go back that on the very, very last slide. So I'm not touching on this anymore, but so this seems to be an interesting relation. So yeah, it is actually used as a privacy mechanism. This channels in a work by Ellingson et al. And they look at this rapport scheme, which is a Google-based privacy scheme. So what they do is, if you use a Chrome browser and you want to feedback some information to Google, they use this privacy mechanism. They use epsilon differential privacy. So they run a Bloom filter on your response. Maybe there's a problem with this browser, and they run a Bloom filter on this response. And on the bits of the Bloom filter, they run 2 binary symmetric channels cascaded to ensure privacy, actually. And then they show that this is epsilon differential private by this mechanism. So this is actually used to generate privacy, actually, differential privacy. So now, okay, let's go back. Let's do something different for the time being. As I come back on the very last slide, in the conclusion, because we have a conjecture revolving around this. So in this talk, what we do is we look at rate distortion codes with the privacy constraints. We look at codes which give us this rate distortion bound, or this rate distortion behavior with some additional privacy. So we have a special setup. I'll explain this in a second. And we look at the optimal trade-off between privacy and utility with respect to the definitions I'm introducing on the next couple of slides. And this is actually for the case I discussed with Lalita, where we have rate optimalities desired. So for example, if you think about distributed phasor measurements in a network, and you want to actually compress these phasor measurements, but in such a way that there's a privacy constraint. So maybe the power network is shared by several companies, and you want to compress it that there's a privacy constraint. Maybe you want to leak some information to the other company, but not all the information. So rate optimality is something which is desired here, and that's why we can use rate distortion codes. So and what we do is we do the optimal rate distortion equivocation trade-off, and based on the construction of polar codes, which I'll explain actually in a second. So there have been a significant amount of literature actually on this. So this is a Yamamoto scheme, which we're actually following very closely. They looked at the information theoretic boundaries of this rate distortion equation privacy for the problem we are considering. There are two-way source coding with privacy constraints by Lalita and co-authors. Utility and privacy for database have been well studied. I guess I'd only arrived yesterday here for the workshop, so maybe this was already discussed in the first couple of days during the week. And there's a connection of differential privacy, lossy source compression, recently by Anand, Lalita, and by Poincaré. So there's many more, and I apologize for all the references I've missed here. So this is the source model under consideration we're looking at, and this is actually related to what I've shown before, which is a simple toy example rate distortion scheme. So what we do is we have an IID source. The IID source generates correlated pairs of random variables x and yn. So we get a vector x and yn. Again, everything is IID here. And again, x and y are dependent. We have a source compression scheme, and we generate an index w. The source decoder only reconstructs x hat, but we don't want the source decoder to get any information about yn. So yn, is correlated with xn. So obviously, if there's a strong correlation, the source decoder would get some information. But by using source encoding as a kind of privacy mechanism, we just have seen, by adding distortion, we can actually have this test channel and flip these bits on test channel. So add noise. We hope that this will help actually keeping yn private. So you can also see this another way. See that this basically is a compression, and this is a kind of function computation here. So this, for example, this w is sent to the cloud, and the cloud operator is only supposed to get x hat n, but it's not supposed to get yn. So it would be kind of a secure function computation in the sense that it's a very limited function computation. The function it computes is only the reconstruction function here. So is it clear so far? Problem? Yeah?
I guess one question. To tie back to the talk that you missed, Ya's talk, and also I guess Lilith's talk, right? So here you're assuming the source encoder gets both x and y.
Right.
And what Lilith talked about the encoder only got x. And these are the two setups in the thing that Ya talked about, where there's full information, or what do you call it, full something, full data versus what he called output per
Yeah, yeah. I missed that talk.
Think about it, but okay.
It's statistical knowledge versus statistical knowledge of correlation.
Well, yeah. Well, let's just be concrete. Let's just be formally mathematical about it and just say there's x and y, and you either know both of them or you know one of them. And here you know both of them.
Yes.
And you're only going to consider that case.
Yeah. Right. Yeah. That's
So
true.
that's
We know both of
data
them. Yeah.
case, so-
Yeah. Yeah. I missed that talk actually. Yeah. Yeah. Okay. Yeah. Right. Okay.
In this effort to try and make this
So
consistent.
my work considers both.
Oh, you consider both. They're two different setups.
All right. But the rest are more questions. Is clear the setting so far? Want to consider?
So what would be your example in the cloud where is y and what would be x?
Okay. So think about the cloud as typically if you want to do computation, you want to hand it off to the cloud. And here, the computation you might want to hand off is source decoding. So you source decode. So typically, we think about function computation. It could be a general extension of this model. This is a very specific approach.
No, but I'm asking, what kind of data are you looking at where you're talking about X and Y?
I mean, data, for example, could be that Xn is a public information, Y is some private information. For example, if you think about this phasor measurement approach, right? So there might be some data which is public, some data is private, right?
You know where the links are, but you don't know what the phasors
Right.
are.
For example, I mean, you might think about, you might come at some for example, this video, this example, this video example, right? You have a video, you have a base layer, and you have a private layer, right? So Y and X would be the base layer, and Y would be the private layer of the video. And then
PMU, maybe you want to use some other data in the grid, but PMU is just basically just voltages. So if you share everything, and you cannot hide some, or you're hiding some subsequence, and that may not be so correct. So just clarifying this.
right, or
It's
it could.
easily compressible because it's on a sine wave.
Right.
So
It could be also. You could be also. If you think about a CRAN, like in 5G, where people you offload computation to the cloud, and so you have to compress data, basically what you get, and you might only some data need to be kept private from the cloud operator, maybe the user data, credit card information, and other data might be public, right? So I mean, this is somehow a relation. So this problem is, I think this problem is very generic. It shows up in many situations actually. That's why we looked at this. So. I said it's an instance of a private function computation with a very specific function. So one of the goals actually to extend this problem to general function computations in a secure way. This is ongoing work I'm describing today. So now again, utility measure is Hamming distortion here, and I just mentioned this. So our utility is distortion, and our privacy measure is actually equivocation. And equivocation is basically, if you look at the source coder, so he sees W. So what can he get? How much information about Y can he get from W per symbol, right? And of course, what we want this to be maximal, to be as high as possible, to leak as little as much information about Y as possible. But of course, now people say this is not an operational measure. Actually, we have some simulation results at the end of the talk where we can actually show that we can measure this, or we can estimate this pretty well from the data. Even if it's n-letter information, so you cannot really estimate with histograms, you have to do something different.
That's just a minus sign there.
Oh, there's a minus sign. Yeah, sorry.
So
I know,
my
yeah.
question is, are you assuming your data is binary, or could be any arbitrary source?
The data, we can do it for any arbitrary source, but we currently have run it only for binary. The reason is because implementing polar codes for non-binary is a little bit cumbersome if you have only implement that for the binary case.
Oh, I guess, so, okay, never mind, I'll see.
Yeah, there's the typo, sorry. I changed this slide yesterday after there was some criticism about accessibility of the talk, so I guess I'm with my jet lag and my sleep deprivedness, I forgot the minus here, so apologize. And there might be some more typos actually. So,
you can fix them before the video is posted.
I know, yeah, that's a good idea. You can fix them on the way back. So, okay, the question is what we want is we want to look at the rate distortion equivocation region here. Again, that's what Yamamoto did, and we just want to iterate his results. So what is the best trade-off between the communication rate or the compression rate here for the W? Again, recall the W has NR bits, the utility measure, and the privacy measure. Right? What is the best possible trade-off? And it turns out that this is actually the result by Yamamoto, so which I have here in the theorem, way back in 1983. So he says if he had designed the rate distortion equivocation region as a closure of all these triples, R, D, and delta. So delta is the equivocation, D is the distortion, and R is the communication rate. So if all these quantities are given in such a way, so these are actually the boundaries of these regions here, these quantities on the right hand side, for this joint distribution here, then we have this rate distortion equivocation region, where if we, within this region, if we outside this region we are fine, and within we are, it's a three-dimensional region, within we are not, it's not permitted.
Source distribution.
What's it?
Q hat is your source.
Yeah, Q hat. Sorry, yeah, Q hat is. So I think it should be X hat here.
That's what I thought.
Yeah, it's X. Again, there are some typos. Apologize. So, yeah, the Q hat is the source distribution. QXY. Q is the source distribution. I think there's no hat here, right? So the hat is gone. Yeah. So I guess another typo. So I guess who was the most typo? I find the most typos. I invite you for lunch or so. Right? So. Okay, so and this.
What's up with the comparison? Okay.
So this is actually achieved by random codes. So this now actually what we have to do is for each joint distribution QXY and each demand, actually we have to find the optimal function here, which minimizes, or the optimal test channel here, which minimizes the rate expression and maximize the equivocation expression. So by the way, with the equivocation expression, I changed things a bit here. This should be actually W, right? So, and okay, so this is a standard problem. Actually, we don't. It's a standard problem because both these quantities. This is a convex quantity. This is a convex quantity. So we could do that. Now this is an example how this looks like here. So let's look at a doubly symmetric binary source. So X and Y are correlated with the Bernoulli 0.5 distribution. Sorry, X is a coin flip and Y is a coin flip, and X and Y are Bernoulli P. Sorry. So if we add X and Y, we get a Bernoulli P distribution, and both X and Y are coin flips. So in here we have the distortion versus array versus the equivocation. Again, the uncertainty at the decoder to estimate Y hat. So clearly, if the P is a half here, then X and Y are independent, and we can actually get this one here, right? So, and if we increase the dependency between X and Y, we get lower here. We get down to, so we actually lose in equivocation with distortion. And this is actually the rate curve, the distortion over the rate. And if the P is 0, then simply have the standard rate distortion problem I just presented before. This is exactly the curve I just presented at the beginning of the talk for the Bernoulli half source. And if we increase the P, the curve becomes non-convex. And we have this breakpoint here at 1 minus, I guess it's 0.5 minus P, which is 0.25. So this is this breakpoint. And so we actually see other curves like this also, right?
I have a question.
Yeah?
So, you might talk about this, and it's actually in my paper, original paper, actually. So, and I have some conjecture. For some sources, if you have mutual information xy to x hat, the rate distortion mechanism will optimize also px. It'll maximize the equivocation.
Yes,
but in
true.
General,
yeah.
This is not.
In general, it's not true. Yes. Yeah. In general, it's not true. Yeah, exactly. So for some sources, it works. That's why in general, you have to look at this region, right?
Yeah, especially for the Markov chain, yx hat.
Yeah.
Then the rate distortion.
Yeah, we are not. Yeah, we are not looking at this Markov chain. So we have a general. We are not. This is easy, right? This case,
but in this case, actually, you will always find a different distribution.
Right. Exactly. If you have a Markov chain yx hat, then it's easy. But no, we are looking at this giant. But it's
not always true that
it's
the distortion
more.
mechanism optimizes.
But yeah, but it's more tractable actually. The problem. Yeah. Yeah.
Right, so looking at the plot on the right, normally we think about being able to time share to convexify rate regions. So why is time, so you would use, for those who don't know, you would use like a code, you'd pick the blue curve and you'd pick a code that works over there, which gets distortion 0.1, and with rate 0.6, and then you'd use that half the time, and then you'd use the one with distortion 0.3 and rate 0.2. And then you sort of use each of them half the time, and by convexity, you get something kind of like halfway through, which is below the.
Yeah.
So you're also asking an example, right? In this paper.
So this point comes from the fact that you split this channel up into two channels, which the one for x equals y and the other one for x unequal y, and this channel for x unequal y first doesn't have any, so this is the point where the distortion of the second channel kicks in. So that you can
actually exactly at 0.25.
Yeah, it's exactly at 0.25. So you can think about this. The first channel at this, you have the first channel. So you have two parallel BSCs. The one you use for if x and y are the same, and the other one use if x and y are not the same, and the probability that this happens is exactly this probability here. When the first channel is selected and the second channel is selected.
There'll always be a chain.
Yeah.
So essentially there's a good strategy here, one code here, and then one code
Exactly, yeah. One code here, and then basically the first channel up to this point, the first channel already is exhausted, so it's already 0.5 crossover probability. So you have to use the second channel to increase the distortion, actually, the overall distortion.
So I guess one interpretation would be, okay, so you say it's exhausted,
yeah.
You're saying that, okay, if X is your political preference and Y is whether you own a gun or not, being very American here, you know, you, at some point you're like, oh, what would I say? It's like, for one class of people,
yeah.
It's more correlated.
you would just say, I'm going to report random, like completely independent.
Right. Yeah, exactly, right. Yeah, that's, yeah, right. Well, you want to help you would complete random, and then you would start on using the gun thing, right, at this point. So and then you cannot really do time sharing. So that's how this peak comes into play. Okay, so this is not really, this is still the preface. So now I have to bother you with some coding theory. So I understand this might not be the main focus of this talk, but in the end we go back to the privacy case, and I hope I make it almost clear what's going on. So now we completely look at a completely different problem. Look at the channel coding problem, but as we see, it's very related to the problem we are studying, the privacy problem actually. So we look at polar codes, right? And this is the phenomenon of channel polarization, which is the basis of polar codes. And so if we consider W as a binary symmetric channel, so this is a channel W here, and this is one ingredient. The second ingredient is a random n by n matrix, which has a length of integer powers of 2. So this is my matrix here. This is my input U, this is my output X. It's a random n by n matrix. I put them together, a so-called channel combining step. So what happened is, now the goal is to reliably communicate over a noisy channel, right? Forget about privacy, forget about source coding. Now we do communication over a noisy channel. So over this guy we want to communicate, over this W. So what we do is we stack those channels at the output of this G here. And this is called the channel combining step. And then we do, first of all, we have a vector channel. If you look from X to Y, we have this vector channel here. And then we look at the overall channel from the input to the output. So we have this UN here and dyn. So we create the channel from here to here, right? So this is clear, right? What we do? Is it clear so far?
So should I think of GN? Should I think of GN as just the parity check matrix of the?
No, it's no parity check. It's just an n by n random matrix.
Oh, it's just a random.
Yeah, it's just n by n. Don't forget about no parity, nothing. I mean, it's just an n by n random matrix.
Scramble the bits of U to create.
Exactly. I mean, say.
Into a channel that flips the bits of probability P, and I get Y.
Right. Say, suppose this is a binary channel, and this would be a binary n by n matrix, right? So you can pick them as you want.
So is this like looking at the source coding problem in the reverse?
Yeah, I know that we are getting there actually, but first of all, we do channel coding, right? So something completely 180 degrees orthogonal to the topic of this session here. But now this preserves the capacity, right? So if we look at these channels, I've said these are symmetric channels. They have capacity CW, and I take n of those guys. So this would be the mutual information between xn and yn, right? So here for those guys. But this U is a random transformation, so it's really a random mapping from U to x. So this is equivalent to the mutual information between un and yn. So basically, the capacity of this vector channel is n times CW. So we don't lose anything.
GN is known as the decoder. GN you're saying is random. So do I have to say?
We are not talking about a decoder yet. This is just a general model, right? So GN is a general.
Averaging over the distribution of GN, or am I saying with high probability for okay? So GN.
No.
GN is a random matrix with some distribution.
You'd average, right? If you average over the whole distribution of GN, okay. Right? So uniform. You pick those zeros once, uniform, and average over everything. So essentially, now we do another step, which is called channel splitting. So this is our structure we have here. So what we do is we take this guy we have just seen and apply the chain rule, and then we get this thing here. So
You mean conditional?
yeah, so there's a condition. Yeah, so this is a chain rule, right? There's a conditioning. Yeah, there's a conditioning on UN. Sorry. Yeah, again, that's not there are typos. So you're right. And so basically, we define bit channels from WI. These bit channels WI defined from UI. Now this is the first guy. Say U is 1, U1 to Yn. And if you pick U2, you find a channel from U2 to Yn and U1. So this is the previous use, right? So this, you define those new channels which map Ui, and the output would be Yn and Ui minus 1. Right? So this is a new, and this is called channel splitting. So what we do is we split this up again. And then we have those new channels here. This is the first channel from U0 to Y1. This is the second channel from U1 to Y1, U0. These are the other channels actually. And you can always see that the output is always the previous use we have not considered in this step. We have considered in previous steps, right?
Is there a reason you're 0 indexing now as opposed to 1 indexing?
It doesn't matter.
Okay.
It doesn't matter. It doesn't matter. Okay, so this is again the structure here. And now something very funny happens. So if n goes to infinity, so if you basically stack infinitely many of those channels here, because this big capital N was 2 to the small n, then those channels become either a wire or become perfectly noisy. So they're really like a wire have capacity 1, and some of them become perfectly noisy. So it's really like this phenomenon. So what you can simply do is you can say, I take the channels which are a wire and transmit uncoded bits, and the noisy bits, I don't transmit anything, or I transmit some prescribed numbers the decoder knows, right?
So again, this is
average over the G. And this actually, the fraction of good channels approaches the capacity or the symmetric capacity of this channel W. So basically, recall the channel W was the channel we started with, the one we want to communicate over. So, and this actually recovers channel coding theory, where we also average over the whole code book, right? So this is actually the same. So we have a random matrix, and we average over the code book. So now, as said, we transmit uncoded bits over the good channels and freeze the bits in the bad channels. And the decoding is done by successive cancellation. In the interest of time, I'm not talking about this, but what you can see is, to get an idea is, the decoder would see Yn from the structure and would recover U0. Then the decoder would take again Yn and take the U0 it just recovered and recovers U1. So it goes in a zigzag fashion here. So basically, the decoding result of the next stage always relies on the decoding results of the previous stage, and this is successive cancellation. Okay? So this is a channel polarization. Any questions so far? Is it clear? Clear to you guys?
I guess from
yeah.
So okay. So this is average over G. So if I draw a random G, there are a couple of questions like, is it true that with high probability over my realization of G, that the fraction of the channel is concentrated?
Yes. Polarization is unavoidable. And how do you say it? Unavoidable, yeah.
Okay,
it always happens.
So if I pick a random G, then with high probability, I'll get
right.
But is it, for a given G, how hard is it to figure out which channels are the good ones and which channels are the
Okay. So this is, you can do that. We are not yet there because we have a random G. There's no structure still in this G, right? I'm talking about this next.
Sure.
So if there's structure, it's easy. Or there's an algorithm, you can do that. So
okay, so
there are techniques.
If G has a nice distribution, then there's an efficient algorithm for figuring out which of these U's are
exactly.
lousy and which of them
exactly. And that's the beauty of the whole thing, actually. That's where you have to put in some work, actually. There's some approach by Tal and Vardy, for example, upgrading, downgrading channels. You can use this. So it's very nice. So anyway, so again, this is still a random matrix, right? Random matrix is a very high encoding and decoding complexity. So what we need an efficient matrix operation. We need to bring some structure so that the whole thing also works. So sorry, yeah. Is it? 10 minutes. Okay, I have to speed up a bit. Okay.
Yeah. Started 9:25 maybe.
So 9:20.
We started.
So 20 minutes.
20 minutes.
Yeah, 19 minutes.
Okay, that's better. I thought. Okay, so now we look at a systematic construction.
Because we started at 5 minutes.
Okay.
Yeah, sure?
Yes.
Okay, good. So now we start a systematic construction. It's fine, so I'm lucky. So we have a systematic construction here. So let's look at this matrix G here, very innocent matrix. And now what we do is we take the Kronecker product with itself. So where the 1 we plug in a G, and then we actually get this one. And now again, we take where the ones is, we plug in again this G, this 2 by 2 matrix. We get this here, and then we get this one. So, and now basically, you can see how this construction goes. You take basically where the ones are, you put in these small g, and do a Kronecker product, and this gives you a systematic structure, not a random one. And again, the side length are always integer powers of 2 here of this matrix. But still, what you want to do is you want to have a good code. And again, anybody who knows coding theory knows that we need to have a smaller number of rows and columns to add redundancy. And we pick exactly those rows which correspond to these i's, for which these channels I've presented before are wires, are noiseless. Right? So in this case, we'd assume that 3 channels are perfect and the other channels are noisy. So we exactly pick those rows where those channels I are noiseless actually. Right? So and we use those rows, so we commute data on those rows, and the other rows we ignore basically, we kick out of the matrix, and we just transmit junk or some prescribed number the decoder knows.
So I don't quite understand why. I mean, I see if you look at those 4 rows that you chose, you have they're very structured.
No, I chose them just random. You can pick any other row. It really depends on the channel you look at. Right? I mean, it's not just I chose these rows. I just chose these rows for exposition. I could have chosen any other rows. Yeah, I could have chosen all the first 3 rows. It depends on the channel you're looking at.
Okay.
Right? So, and again, now if we do that, we can show that the encoding and decoding complexity is not n to the power of 3. It's now under n log n. So it's very, very low complexity by using this structured construction here.
Sorry, the blue rows are the noisy rows, right?
No, the blue rows, yeah, it doesn't really matter. I mean, the blue rows, I said they are the noiseless rows, but you can think about the noisy rows too. I mean, it really doesn't matter as long as you know which rows to take out, right? Okay, so basically there are 2 properties of polar codes. We have a low encoding complexity. That's kind of nice. And the problem is the error probability scales with a square root of, so there should be a minus n. That's again a typo here. To the minus square root n. So it doesn't go down with 2 to the minus cn as we wanted to have, even for a small c. It really goes down a little bit slower. And that is really the problem with polar codes. So there's a minus. So again, another typo, I guess. I need to fix them all. So now let's get a bit technical because, and unfortunately we need this. I just try to be a little bit brief here because it gets a bit technical. So now we have seen what we have to do is we have to partition this, right? So this is a set of all U's, and we have seen some of the channels are good, some of the channels are bad. So the bad channels we call frozen channels, or the corresponding bits we call frozen bits, and those bits we just allocate with any number and send it to the decoder because we cannot communicate over these channels reliably. The information bits are associated with channels which are perfect, right? So we can transmit information. So, and we say that these channels are almost deterministic given the previous use and the yn. These channels are almost random given the previous use and yn. This is for symmetric channels. But now, again, what Lalita said in the beginning, sorry, in a second, let me just finish this. And we want to reverse this and want to use this for source compression. But for source compression, it's not enough if we just compress uniform sources, right? We want to really compress any source. So as a consequence, we have to go from symmetric channels to asymmetric channels here. Again, you have a question?
Yeah, I have a very different question, but I think maybe I'll ask
Yeah, okay, right.
Tell us how the code
So now we look at asymmetric channels. So we need this actually for running source coding over asymmetric sources. So here we have to partition this into 3 slices. The problem is basically that, okay, there's something cut off, sorry. This is should be almost deterministic given u from 1, I minus 1, and almost random given ui 1 minus 1. So basically, this is the partitioning we had before from here, but we have a new partitioning because if we have asymmetric channels, we also have to look at the distribution of these ui, these vectors from u1 up to ui minus 1. So so we get these 3 sets here. So these are again the sets where we have the frozen bits. These channels we can communicate. We cannot communicate. These channels are super noisy. These channels here are perfect as capacity 1. We can transmit uncoded bits, and those channels we not use it for communicating. But what we can do is we can estimate the bits at the decoder from the previous guys because these are almost deterministic, given ui minus 1 and yn, but they're also almost deterministic given and this is missing, sorry here, ui y minus 1. Right? So they're almost deterministic given the previous bits. At the decoder, when we have decoded a whole string of bits already in the successive cancellation, we can simply decode bits in this area here by looking at the previous bits, u, and simply determine them with high probability from these previous bits. Right? So these bits are kind of it's kind of a low entropy set. You can think about this as a kind of entropy here of the individual sets here. So the L would be low entropy. No, L is simply indicates low entropy, so low entropy bits. But now we have to intersect this because this region would be the high would be hx given y. This would be lx given y. But now we have the hx here, and we see that in the uniform case. In the uniform case, if the input distribution of the channel is uniform, then this hx would cover everything here, would cover basically the whole thing. There is no lx, because if it's uniform and we compute the entropy, we actually get 1, right, if we binary case. So we need this third region, actually. So, and now this gets a bit technical. I just want to tell you that we can compute these regions here based on some parameters of the code, which is called Bhattacharya parameter. I don't want to talk about this because it gets a bit technical here. So we'll be able to do this. And now we go back to lossy source compression, not just, again, privacy, go back to lossy source compression. Now say that the idea is basically to take the noisy source sequence, or the source sequence we want to compress, as a noisy code word from some fictitious polar code. Right? From some polar code, so we get a sequence we want to compress. We think about nature has used a polar code word, and added some noise and gave it to us. Right? So, and what we can do now, we can apply a channel decoder as a source encoder by applying, for example, successive cancellation. So we run this polar decoder. And we can do that actually because if we look at this here, this is our test channel, our inverse test channel I've just discussed. So these are the bits from nature, right? And this is the noisy bits from nature, and this is the corresponding reconstruction. So what we want to do is we want to really run a polar decoder to get back these guys here. So basically by running a polar decoder, we would quantize this to the nearest polar code word at the encoder. Right? So this is a kind of vector quantization we do at the encoder. And it's a very nice vector quantization because we can have a very low complexity of order n log n. Right? So, and this is the encoder we are using here. And right, and then at the decoder, at the source decoder, we would simply take this u, which would be the output of the encoder, and multiply with this gn, and get our code word back, our constructed code word.
How do I know what G to use?
Okay, so you have to know the test channel, and that's a caveat, right? So you have to know the distribution px, pxy, or pv, comma x hat, right? And then design. That's the big caveat which doesn't make it universal. So in the sense of it really, I mean, even we can say we can prove differential privacy at the end for each distribution, we still have to design the code separately. But that is something we might go away by using universal codes, actually.
So this is just without the privacy problem, right?
Yeah, no privacy yet. Right. So I'll let you know when we have privacy. Right, so, and now becomes the privacy problem again. So now let's go back to the privacy problem. So I apologize for this detour into coding. So this is the problem we want to solve, essentially. Now our correlated sources xy combined as, okay, this should be here, actually. I changed some slides yesterday, but you shouldn't do it if you're tired and it's late and you have to go to bed and stuff. So again, this should be x and y are now combined to v. So in the previous thing, so this setup, this is now my x and y combined here, right? So yeah, here I have it again. So the test channel is now given as, or the inverse test channel is given as, no, this is actually the test channel. This is a test channel here. That's it direct, right? That's p, yeah, p, it's a test channel, right? It's p x y given x z, yeah. So now how does encoder and decoder work? So again, and I don't want to go into details here, but simply what we do is we have these three different sets. Just presented before, we have a white set, we have a red set, and a blue set. And the red set is the fine set. So this is actually what we put in the red set. These are the data. And this is the frozen set here, the frozen bits we select. And this is actually the white set. And what we simply do is we do randomized encoding in a way that we generate those distributions here. And simply the output of the coder we decide by a conflip based on these probabilities here. So it's randomized encoding. And the decoder, we take this U, we convey this to the decoder, and the decoder simply copies the U, which is the data in the red set. And for the blue set, the frozen bits, he simply uses the frozen bits. So these functions F, they are pre-allocated to the decoder and the encoder. And for these sets, this is a white set, right? These are the bits, UI, which can be decoded from the previous bits at previous indices with high probability. There should be UI here, sorry. And no, actually, U is fine, actually, sorry, U is correct. And simply use an argmax rule here for this one. So, oops. Yeah, so that's correct.
Something I'm just a little confused about.
Yeah.
So for the polar coding construction, the channel W, the one that, the noisy channel over which you're trying to communicate, the output alphabet of that is just anything that you want.
Yeah.
So when you do this reverse thing, you can put a pair XY
Yes.
and set that as the output because the output alphabet. So how does the decoding complexity, you said it's n log n, is it like n log n times the size of the output alphabet? Or is it, I mean, does the size of the output alphabet matter? Like if my y is a real number, presumably things are a little trickier than
it does not matter because it's just a different computation of the log likelihood ratios. Okay. It's just if you have a communication, take a Gaussian channel, instead of taking the Gaussian channel, you quantize the Gaussian channel, the output. Right, but you still have the same.
So you just do some processes and make it finite?
Yeah, I mean, yeah.
Okay.
So that's simple. And the only thing I forgot to say why we do this construction with the using a code from nature sounds a bit weird. The only thing why we are allowed to do that because we know that those bits are IID here. Because for any code, and that's what you have to prove. If you want to use a channel code as a source code, you have to prove that if the input, if these bits are IID, that those bits are IID too. And we do that because of the special structure of this matrix, even if we chop it off. Right? It does not work for all codes. It works, for example, for LDPC or LD low density generator matrix codes. You have to prove that it works too. It does not work for all codes, right? Because typically if you have a convolutional code, the output bits are not IID, right? Because you average over the whole thing, and then it does not work. So that's actually something. It sounds a little bit magic, why we can use this. Some fictitious polar code that only works because this is actually IID. So now, okay, this is the encoding decoding, and now this is actually our main result. We say if we have this polar coding scheme, or if we pick any point in this region here by this joint PMF here, a rate, a distortion, and equivocation, then actually our polar coding scheme can give us a rate which is a little bit smaller than this one, or which is actually star plus epsilon. The distortion is a bit smaller than this one here, and the equivocation is a bit bigger than this delta. Right? And these terms are very small terms, order to the minus. Actually, it's order to the minus square root of n. So this beta is a half, or it's smaller than a half. So these rates are achievable by the proposed polar coding scheme. So basically, the polar coding scheme does the job. So how much time do I have actually?
You have 10 minutes.
10 minutes, okay, great. So let me just briefly explain how I prove this.
You started almost 10 minutes.
So 10 minutes, okay?
I'll give you 7 minutes.
7, okay. Yeah, so I have to speed up a bit. Okay, so.
Because it's cutting into the.
Yeah, I understand. So, okay, so we just show how this can be done. So I introduce 3 distributions, and I'm a bit brief about the proof here, because it might be a little bit involved. So this is a distribution we want to mimic by our scheme. So this is basically the distribution which essentially comes from a random code by Yamamoto. And we have an induced distribution for our encoding scheme. And we see that here we have the encoding operations here. So we have the D set, which is this distribution. We have the I set, which is the set where we transmit our data. And we have the frozen bits. And we look at the frozen bits uniformly IID, so we randomize over all frozen bits. Again, this is what Anand said now, we don't randomize over the whole matrix, randomize over the frozen bits. But in the next step, we remove this assumption. But for this step, we randomize over the frozen bits, that's why this term is red. Then we do that also for the decoding scheme. So the decoding operation shows up here. So you have these three distributions. And essentially, in a nutshell, I skip a couple of steps here. We can show that the expected distortion over the decoding distribution here can be upper bounded as the intended distortion we want to have d star plus a term given here. And this includes the variational distance, the L1 distance between the distribution P, the true distribution from a random code, and the distribution done by our encoding scheme. But we only have to show that our encoding scheme does the same as a random code. Right? Then this variational distance will go to 0. So, and we can show this actually that this variational distance is small. Actually, it's 2 to the minus n to the beta here for if we select the frozen bits uniformly IID. And the main proof ideas are that this only hinges on the frozen sets. I don't want to talk about this in detail. We average over all bits in the frozen set here. That's the main idea why this works. So
it matters that you set the frozen bits to be IID and not just 0?
Okay, at this point it matters. In this point it matters. At this point we have to average over frozen bits. No, right. I mean, we cannot. I mean, but in this case, we would have to share randomness between encoder and decoder. So this gives us a total distortion here. And again, it's average over the frozen bits. Now for the equivocation, so the equivocation, now this means that we again take the expectation over all frozen bits. So it's the expectation over the function QD and average over all frozen bits. So we can write this actually in a form that we can express it with the function with a QE. So this is a distribution at the decoder, induced distribution at the encoder. And this can be upper bounded by this expression here, which can be essentially upper bounded by this expression. So this is again close to what we want to have. This is xn hat and this is yn. Still, it's not. We are not yet there. So because
that's an upper bound, right?
Yeah, no. This is a lower bound actually. This is a lower bound. So what we want to show is essentially we want to show that this HP, the equivocation by the true random code by Yamamoto's code minus the equivocation by our code is actually very small, right? So and we can do that actually if we assume that this variational distance can be lower bounded by this expression, and then we have this from our polar code scheme, and then we use actually result from Shizak-Körner to show that this is actually, you get this. So, and that you can see actually that the equivocation is also very, very close of the scheme to what we have in real life. So, and again, it's average over the first of chosen bits. So how to obtain the equation for a fixed set of frozen bits, because this isn't really useful, right? So we want to have a fixed set of frozen bits. So these are fast 7 minutes. So fast 7 minutes. Anyway, so a fixed frozen set. So what we do is basically for the equivocation, we assume that this is our ray distortion plane here, and we know that this is if we like the expectation, all these values, ray distortion points, must be in this pentagon here. And particularly if you look at a point here, we can obtain a point here, which is actually a good point because it gives us a distortion smaller than our expected, slightly smaller than our expected distortion, and an equivocation slightly larger than what we want. We can do by time sharing of this point and this point. So we only need 2 sets of frozen bits, UF1 and UF2, and we do time sharing. We're always in this quadrant. And by doing so, we can actually achieve, by time sharing with 2 sets of frozen bits, we can actually achieve these results for a fixed number of, we don't have to average over all frozen bits. So these are some experimental results for the ray distortion. We use a double binary symmetric source. This is the ray distortion bound, as we have seen here. The P is actually 0.1, so see it has this non-convex property. And we see that we get very close to this bound if we increase the block length. So that's kind of obvious, but what about the equivocation? How to estimate the n-letter entropy? So, and what we do is we use Lempel-Ziff to estimate the n-letter entropy, and for any vector xn which is not necessarily IID. So, and how this goes is basically how Lempel-Ziff goes is we take a window here, and in this window we find the string in the next, so we look at the string here in the next element from, so this is the window, right? And this is our data, and we shift this window, and we always try to find the string which is actually in this window. And look at this length. And what we can do, the length of the longest match, we can show actually that this, if you explain this, that actually converges to the entropy rate of the process. It's a result by Kontonianis. And essentially, if you do that, estimate the entropy like this, we see actually this is the equivocation here for the rate distortion for theoretical bound, and we get those rates here. These are the entropies induced by our polar code. So these different colors depend different block lengths. So we get the closest actually here by using a long block length. So we are not that there. There's a bigger gap, but we can also see that the longer we make the code, the closer we get to this joint entropy. So this actually concludes. So I've presented a polar code as a constructive approach for achieving the whole rate distortion region for arbitrary source distortions. Again, we conjecture that the scheme is epsilon differential private for some distribution qxy. And the reason, what the intuition here is that if the qxy is a symmetric channel, a qyx is a symmetric channel, again, we can split this up in two binary channels. And for each binary channel, we can find the epsilon differential privacy quantity as I presented on the first slide, the beginning. And we just have to maximize over which one is the biggest. So that is the idea for distribution qxy, for symmetric distribution qyx. For any other distributions, we are far off, and we are still working on this problem. But I think there is there's a big indication that this scheme is epsilon differential private for many distributions. There are, for example, some distributions which doesn't work if you have a Z channel, for example, something like this, between the sources here, x and y. Then this scheme won't be epsilon differential private because this edge is missing. So we can show this actually. So there are some indications that it works for some source correlations, but not for all. And that's all I wanted to say. Thank you.